Hi, and welcome back to our structural training. We're going to go ahead and kick off part 3 of the structural training provided by the City of Santa Clarita. We talked a little bit about beams and beam behavior. We talked about floor and roof diaphragms in the last section, and now we're going to move on. We're going to talk about shear walls. Now, just like the other components of our structure, let's first start off by talking about the physics of shear walls. How do shear walls behave? Now, floor and roof diaphragms that we talked about earlier behave like beams. Shear walls are a little bit different. They don't really behave like simple span beams. They behave more like a cantilever. And what you'll notice is in a shear wall, the shear force transfers from one end of the shear wall to the other end, or from top to bottom. Seismic forces in a house are generated up high, and they've got to be safely transferred down low. So this isn't like a beam where you have load acting along the length of the shear wall and equal reactions at the top and bottom. The way it behaves is all the force comes into the top, has to transfer through, and then come out through the bottom. Now, the reason why that's really important is because unlike a beam, there's a lot less room in a shear wall for things like cuts and notches and openings. In a beam, because it's being loaded uniformly, you've got certain zones which have higher stresses than others. In a shear wall, this isn't so. In a shear wall, anytime you have horizontal shear, you have an equal amount of vertical shear. Thank you, Isaac Newton. Anytime you have an action, you have an equal reaction, not only at the corners, but also on the other side of the wall. So any shear force acting here is going to generate a shear force here. Any shear force acting in one direction creates an equal shear force in the other direction and on the opposite side. And if you're a builder and you've ever cut a hole in a shear wall, you'll know that inspectors don't like that and engineers don't like that. A hole in a beam can be done if done properly, not a big deal. But a hole in a shear wall or altering a shear wall is a really big deal, and it's for this reason. You've got uniform force acting through a shear wall. And of course, we call the force shear force. Okay, so in shear wall A has a certain length. We just call it L, and a certain force F. And so that force F creates a certain amount of shear per foot in the wall. Okay, indicated by these arrows. Let's take a look at another shear wall B. Shear wall B has the same force F, but the wall is twice as long as shear wall A. Okay. So what does that mean? Because the wall is twice as long, the shear per foot is half. Intuitively, that should make sense. The longer my shear wall gets, the less stress per foot I've got, and I can expect a lesser shear wall. As a designer or an inspector or a builder, when you see a long shear wall, you're probably not expecting a really heavily nailed shear wall. Whereas when you see short, slender walls, you're probably expecting to see heavy nailing, heavy hold downs. And that's why, is because the shorter a shear wall gets, for the same amount of force, the heavier that shear wall has to get, or the stronger that shear wall has to get per foot. Another thing that's interesting to notice is that the overturning forces on shear walls. If you think about the physics of how a shear wall works, when I push at the top, the wall wants to rock. That rocking force creates tension and compression on either side of the wall, indicated by these arrows. And that's simple to calculate. It's just the force F times the height divided by the length. Or even simpler, it's the shear per foot times the height. It gives you the same answer. Those overturning forces have to be resisted by either straps or hold downs, which we're going to see when we get into the actual design of our house. Now, as the shear wall gets longer, those forces diminish. Not only the interior shear force in the house, but the overturning forces will diminish as well. And so a longer shear wall, less stress and less overturning. And then, of course, any vertical load I have on that wall will also resist any overturning uplift that I might have. And so when you see really long shear walls, especially walls with a lot of dead load, you'll see either very small hold downs or no hold downs usually, because there's just there's no net tension force in that wall. Okay, what I provided here as part of the training is a typical detail that you would see on plans for a shear wall. And you'll see it's just a wood stud wall. I've got 2x studs. I've got a header over an opening, 2x studs, and then double studs or posts at the end. Here's my double top plate and my sill plate. And the shear walls are indicated by these dashed X's. Those would be the plywood panels on my shear wall. And so in this particular diagram, the shear wall would be this piece right here. Now, when I push the shear wall, it's going to generate overturning forces, right? Those rocking forces on the wall. How are those resisted? Hold downs. So I'm going to see a hold down here, and if there's a hold down on one side, remember the forces act either direction. So normally when you see a hold down on one side, you're going to see a hold down on the other side. Unless there's a large dead load here, you're going to usually see similar hold downs on both sides of the wall. Now, if you remember from part 1 of our training, we talked about structures being like a chain, what we call load path. Now, in this structure, it's no different. The force, whatever the force is above in the roof, transfers into the top plate through these connectors. So the force in the roof over here will transfer through these connectors and into the plate. And then the plate has to transfer that force over to the shear wall. So that's our chain. That's a link. That's a link in the chain, the connector. Then the top plate is a link in the chain. If the top plate is spliced, that's a link in the chain. And then it goes through the nailing and then goes into the shear wall. And so that's our chain. Now, if any one part, if any one link in that chain is missing or incorrect, you've blown it. You don't have the chain anymore. And so that's why it's so critical to build structures per the plans. And that's why building and safety does inspections and so forth, to make sure that that structural integrity is maintained from the furthest end of the building all the way to the foundation. Now, for plywood shear walls, you get about 140 to up to almost 900 pounds a foot. So you get some pretty high values for plywood shear walls. You can also put plywood on 2 sides of walls to double the capacity. So you could, technically, you could build a shear wall that had over 1,600 pounds a foot of capacity. Let's go ahead and move on. Here's a real-world example of a tract home here in Santa Clarita that illustrates what we were just showing on that figure that we were just looking at. Here we have a second floor and a roof. And then you can see over here we have our shear wall. Obviously the plywood here is non-structural, right, because it's not continuous to the foundation. So this shear wall, this is our lateral support for the house, is the shear wall right here. But again, one link in the chain isn't enough. You need a complete chain. And so let's look at this real-world example and talk about how the forces get to the shear wall. I've got force up here in this shear wall that transfers through this plywood roof. There's nailing into the blocking. Then there's multiple blocks here, and so the blocks are spliced with metal straps. And you remember we talked about the metal straps, the metal clips, in part 1 of our training. That transfers down from one block to the next block through these metal clips and into the top plate. So each foot of this roof has shear, and it's transferring that shear into the blocking and the metal clips. That is then transferred into the top plate, and then the top plate transfers all that force back into the shear wall and then safely down to the foundation. So you can think about the top plate as what we call a collector. And that's a structural term we use for any element where force is building in the element. So let's say there's 200 pounds per lineal foot in this roof. This foot, I've got 200 pounds. The second foot, I've got 400, 600, 800, 1,000, 1,200. And then once it gets to the shear wall, that 1,200 pounds of force unloads into the shear wall. So conceptually, That's what I'm trying to convey to you today, is so when you look at a structure, you can see that behavior. You can see the force transfer and understand. Now, if the top plate was cut right here, and there was not an adequate splice, all the force from this part of the structure has no load path to get to the shear wall. And so this is why top plate splices, those connections we were talking about earlier, are so important. Next example I have here is, here's a shear wall that was an existing building, a plywood shear wall, and our building inspector here in Santa Clarita went out, and the wall had been severely cut, some openings severely compromised by these openings. And you can see, in some areas, I mean, almost half the shear wall is been compromised. Now, when we started talking about shear walls in this training, remember, the force in a shear wall is uniform from top to bottom. It's not like a beam where you can make an opening in a beam and call it good if the opening is in the right place. In a shear wall, each one of these openings in this shear wall is reducing the capacity of the wall significantly. And when I like to call this Swiss cheese. When you turn a wall into Swiss cheese like this, now you've got a situation that does not meet code. And this is something that a city building inspector would write up a correction, and we would require this wall to be repaired in order to make it safe before we allow them to close up this wall. Okay. Another thing to keep in mind, and I mentioned here, simply patching openings in shear walls is usually not an effective fix, because you're not, the capacity of a solid piece of plywood versus patchwork, there's a big drop in capacity when you do that. So on a wall like this, you're probably going to look at replacing plywood panels. Okay, also on shear walls, the new building code offers what we call perforated shear walls, or shear walls with transfer around openings. And this is an example just to talk about the physics of how these perforated walls work. In the older building codes, what you would have is discrete panels. So this would be one panel, and this would be another panel. And the pieces in between the panels, this piece and this piece, would not be a part of the shear wall. They would just be considered extra. And what you would have is each individual shear wall pier, so this pier on the left, would have hold downs here and here. And it would act like its own individual wall. Likewise, this piece would act like its own individual wall, and you'd have a hold down here and a hold down there. What the new code permits is you can actually tie the wall together by putting plywood on these top and bottom pieces and putting steel straps along the top and bottom of the opening. And when you do that, when you tie that wall together, now the whole wall acts globally like one piece. So you can see from the diagram here, tying the walls together, now I've got shear forces in these upper and lower pieces. But the whole wall now acts like one wall. And so when I apply a force here, the overturning on the wall only occurs at the ends. I don't have overturning forces here in the middle of the wall, here or here. And so this offers designers and builders another option for how to build a shear wall. Yes, it's a little bit more work in that you have to tie this together, but you also eliminate the hold downs here. So it's a little bit of a trade-off. And then I've also included a detail illustrating how you would build a wall like this. And you notice that I'm showing the plywood top and bottom, and I'm also showing the steel straps tying the lintel and the sill to the rest of the wall. Okay, so these are becoming more popular. I've noticed on the tract construction that I've been reviewing lately, these types of walls are being used quite a bit more often with the new codes. Okay, that covers shear walls, and we're going to see a little bit more about shear walls in Part 4, see a little bit more of them in action, but now that we've covered the physics of those, before we get into our house in Part 4, I want to talk about gravity loads and switch gears here, and let's cover how the vertical loads in a house are supported and transferred to the foundation. So what I've provided here is a section of our typical house, a section cut through the middle, and I'm showing all of the structural framing of that section. Now, as I mentioned in part one, this is a typical 2x wood frame gable roof. Some people call it a conventional framed roof. Some people call it a stick frame roof is a term you hear. Basically, it's 2x and 2x roof rafters and 2x ceiling joists. Now, there's a few different ways to frame roofs with 2x. But before you set out to design or frame a roof, you need to understand the physics. How do roofs behave? What does each part of the roof do? How does it support the roof? And how do the connections work? Let's talk about a roof framed like this. I've got rafters, but I've got no ceiling ties. If we can go back, we've got no ceiling ties here. Is a roof like that stable? No. If you were to build a structure like this and apply vertical loads on this roof, obviously the physics, when I apply vertical loads, it's just going to kick out. And so that's what we have here. We've had homeowners in Santa Clarita who have cut the ceiling joists in their home. You know, they had ceiling joists running along here, and they cut them. And what happened was their roof started to sag, and the walls of their house started to lean out because that roof is no longer stable. So every roof either needs some ceiling joists or some other type of vertical support. For our typical house, this is the type of roof that we're designing. A standard ridge board, conventional frame, tied roof. Now, notice here, we've added the ceiling joists in. So when I put vertical load on the roof's going to try to sag like this, right? Those ceiling joists on the bottom tie it together and prevent it from deflecting. And that's exactly how these roofs work. When you see a roof that's stick framed, you know that bottom ceiling joist has tension. So the physics of the roof, you automatically know that has tension in it. Okay? But that's not the only way to frame a roof. You can also put a ridge beam in a roof. Not a board, but actually a heavy structural ridge beam. What that does is, going back to this example, when I try to put vertical load on the roof can't deflect or kick down because that beam here is supporting it at the center. So that's a stable structure. And you can have a structure that has a ridge beam here and does not have ties. The ties are really not needed. So the same homeowner who, let's say, you have homeowner A, he cut the ties in his house, he had no ridge beam, and the roof starts to collapse. Another homeowner, if there was a ridge beam there, he could have gone ahead and removed his ceiling joists, and it would have been safe because that ridge beam is what's supporting the load. Now, this is why you get permits for your work. If you're a homeowner and you want to start making changes to your house, come into building and safety. It's not only required by law that you get permits, but this is what we're here for. We're here to make sure that the alterations that you make to your home, to your investment, are done safely and are going to protect the value of your home. And so these are the kind of things we look for. When people come in and they want to make alterations, remove a wall or remove a ceiling, these are the kind of things that we look for. And this is the physics, how it works and why. Trusses behave essentially the same way. In a truss, you have vertical load, and the bottom chord of the truss, just like in a ceiling, in a stick frame roof, the bottom chord of a truss also carries tension. Now, the main difference with trusses is there's all of these vertical pieces, and the reason that those are there is to be able to build the truss out of smaller pieces of lumber. Okay, trusses are very popular when you're building lots of homes. The tracts use trusses quite a bit, and where trusses start to become more economical is in large developments where you're building a lot of homes and they can fabricate trusses, many trusses. Okay, going back to our building section. So our home does not have a ridge beam. It's just a conventional roof with a ridge board and ceiling ties. Now that we understand the physics of structures, we know that these ceiling joists here have tension. So there's a tension force acting on that. Not only that, but any vertical forces that are coming down are being transferred from the roof to the outer walls. Likewise, any attic forces are being transferred from the ceiling joists into the bearing wall here and down to the foundation. Now, the building code requires an attic to be designed if there's headroom in the attic where somebody might store things or put equipment or Christmas decorations or whatever. You have to design that part of the attic for a higher load, 20 pounds per square foot. The rest of the attic, where there isn't room to store anything, you only need to design for 10 pounds a square foot. Okay, so that's why you see these arrows. These arrows indicate the load, and the larger arrows are heavier storage loads in the attic. These arrows, the black arrows up here, are the roof dead and live loads. The tile, when they re-roof, they'll pile tile on. We account for that, and so that's the roof dead and live load. Okay. Now, let's talk about our bearing walls. So this bearing wall carries half the roof and half the ceiling into this wall. And down here, there's a calculation. You can see we took half the roof times the weight, plus half the ceiling times the weight, plus the self-weight of the wall. And when you add all that stuff up, you end up with about 1,100 pounds per lineal foot. Right? As we saw before, our wall studs can more than handle that. This is something we would check on every house, especially two-story homes. Make sure that the bearing walls calculate for the load. But that's exactly how we design it. Now the floor joists are spanning the other direction. The floor joists aren't loading those walls. They're spanning the other way. So this wall here would not carry any floor load. It would just carry the roof and ceiling loads. The walls beyond would carry the floors. Okay, we'll go on. Okay, let's look at some of the specific details for our house. And now that we understand why these structures behave the way they do, now let's look at the details and talk about how. And I think it's going to make a lot of sense. So this detail here, this is where the roof framing comes down and bears on the wall. So you can see we've got our roof rafter here, our ceiling joists, and our bearing wall. Okay. Now let's look at some of the connections. Now we know in our structure that ceiling joist has tension. So that force right there is pulling on the ceiling joist. Likewise, the rafter is in compression. So the force of the rafter is coming down and then being resisted by that ceiling joist. And so this nailing here is designed to transfer that force. And the building code has a table which tells you how many nails you need for that connection. Okay. Now also, let's look at some of the other connections. So we know what the purpose of this nailing is to transfer that tension. Then you've got nailing here, blocking, and framing clips and nailing here. This is that nailing we were talking about with the shear walls. This is the connection to transfer the force from the roof diaphragm into the shear wall, right? Then you'll also have the toe nailing from the ceiling joist to the wall top plate. That's to tie the wall out of plane or wind loads pushing on the wall to the roof. So now that we've gone through and we've laid all the groundwork for how structures behave, we're going to start getting into the details and talking about why it's all there and what it's all doing. So now we understand in all three directions. Remember we talked about thinking in 3 dimensions. Now we understand all the forces in all the 3 different dimensions. You've got the ceiling joist force acting this way. You've got vertical dead loads, obviously, acting this way. And then you've got in-plane shear forces, acting in the plane of the presentation. All 3 of those forces are supported by all the different connections shown in the detail. Now let's talk about the ceiling joist tie, which is happens to be right here. This is where we've got ceiling joist coming in, and then we've got two separate sets of ceiling joists, both framing into one connection here. And so this detail 2 is this detail here. And you'll see, normally when it comes to structures, there's more than one way to design a connection for any given connection. And so I've gone ahead and I've provided 2 different options here. So again, the red indicates that tension force acting on the joist. And you'll see the joist is lapped. This ceiling joist frames over the wall a little bit, and this ceiling joist frames over the wall a little bit, and there's a lap right there. And you'll see that nailing, 6 16-penny nails, right? What is that nailing doing? It's transferring that tension force. When I push on the roof, the ceiling joists are in tension, and so anywhere where those ceiling joists are broken, you've got to lap it and nail it. Same thing as a top plate. Anytime that top plate breaks, you've got to lap it and nail it to transfer that tension. Okay? Now, another interesting thing that you'll notice is, remember we talked about the tension is constant along there, right? So whatever force I have here, I've got the same force here. So looking at our details, I've got 6 16-penny nails here, right? And then on this detail, I've got 6 16-penny nails there. The tension here is identical to the tension there. All right, now here's a common error that I see sometimes on plans is you'll have a ceiling joist where they want to take a roof beam and they don't want the roof beam to poke down into the ceiling space. So what they do is they put the bottom of the roof beam here, and so you get a nice flush ceiling along here. Now notice what you've done. When you push this beam up above, you've broken the ceiling joists. Now there's a gap. Well, to transfer that tension, you've got to give me some kind of a connection. In this case, what's normally done is they'll take a 1-inch steel strap and they'll strap right along the bottom there. Now if that strap is missing, what have you done? You've eliminated that one link in the chain. And remember, a structure is like a chain. One link missing and you've compromised the integrity of the structure. So moving on to the next slide. The last detail in our structure example here is detail 3 up at the ridge, and you'll see in this case we just have a ridge board, and we've got our rafters coming in, and we've got straps. These straps along the top of the ridge board are really provided for seismic forces only. Remember, rafters are in compression under vertical loads, but in an earthquake you'll get potentially some separation there, and so we still require steel straps to be provided over the top of the ridge. All right. Okay. I think we may have talked about most of this. Does the exterior bearing wall carry any floor loads? No. The joists are running parallel. Does the interior bearing wall carry any roof dead or live load? No. This interior bearing wall does not go up to the roof. It only carries the ceiling loads here. So no, the answer would be no. And then the last question, is it acceptable to anchor the interior bearing walls with shot pins? And this is something that comes up, has become more of a problem lately, is whether or not you can anchor a bearing wall with shot pins. And the answer, the code is very clear, the answer is no. The CRC, which is the California Residential Code, clearly states that anchor bolts are required at bearing walls, and there's the code section for you there. We've also clarified this as a city amendment. Now, if we go to the next slide, we'll take a look at some examples of why you don't want to be using shot pins. In Santa Clarita, we are in a very high seismic region here. We're in what we call seismic category E, and the building code is clear that even parts of a structure that are non-seismic resisting portions of the structure still will see seismic force. The term that engineers use is deformation compatibility, meaning in an earthquake, the whole building is along for the ride. Just because this wall is a shear wall and this wall isn't, doesn't mean that the wall that isn't a shear wall isn't going to see lateral force. In the 1994 earthquake, I was here in the city at that time, and the damage in 1994, there were bearing walls that picked up. and shifted and moved, and homes that came off of their foundations. And we had those problems here in Santa Clarita. And so there's a reason why the code does not want you anchoring a bearing wall. So here's a bearing wall with shot pins. Here's an example. This is a bearing wall, and this wall might have, as you're well aware, on a 2x4 wall, you can put about 2,000 pounds on a stud. So that force here, you don't want in an earthquake. You do not want this sill plate moving. You also don't want it picking up. In Northridge, a lot of the force was vertical. And so a shot pin is basically a friction connection. Shot pins are not approved for seismic tension forces. And the code is very clear about that in ASCE 7. You cannot use shot pins in withdrawal or tension. So in this example, anchor bolts are provided. Now here, this was a case where the developer opted to put the anchor bolts in after. Instead of pouring the bolts into the concrete, they went ahead and used what we called a post-installed anchor or a pre-drilled anchor. In this case, they went ahead and they used a shot pin just to set the plate, and then afterwards they came in and they drilled holes and they added what we call Titan HD anchors. And that's just one brand of an anchor that you can use. There's plenty of other anchors made by other manufacturers that can do this same job. But worth mentioning, the state building code in the city does not permit anchor bolts to be, does not permit bearing walls to be anchored with shot pins. We require some form of a positive anchorage or anchor bolt that can support tension loading. Another important item to mention is that posts must be anchored laterally to their base for a minimum of 2% of the vertical load. As we saw in the training before, this 4x6 post could easily have 12,000 pounds on it. And so at the base of the post, you want to have a nice solid connection to make sure that post in an earthquake is going to stay put. Sometimes, an inspector will go out and he'll see a post, a large post, even a 6x6 post. You could put 20,000 pounds on it, and there will only be a couple of nails here at the bottom to the plate. That's not acceptable. You have to provide a connection, a minimum of 2% of the vertical load, and that is clarified in a City of Santa Clarita code amendment. Okay, so this is going to conclude part 3 of our training. We covered quite a bit. We talked about shear walls and vertical loads, and we're going to pick up in part 4, and we're going to talk about globally. We're going to go back to our example home, and we're going to take all these individual elements and we're going to pull them together. Okay, so we'll see you back for part 4.